Hello everyone, welcome to you all in the next video class of physics. So far we have discussed all about charge, Coulomb's force and electric field. Now we are going to enter in a new topic of physics, and that is the concept of potential. So far you have learned in your lower sections that the concept of work, potential energy and conservation of energy were very important while describing the mechanics. In this section we will see that these concepts are just as important for understanding and analyzing the electrical interactions. So let us begin by reviewing the definition of the work, and that was that if a particle of mass m moves from a position A to a position B, then work done was limits from A to B, and it was Fpx. If my force is conservative, then we can again define the work as WAB equals the potential energy at A minus potential energy at B, which on simplifying gives, and we can write it as minus of del U, means the negative of change in potential energy gives the amount of work done when a particle of mass m moved from position A to position B under the action of a conservative force. Now we will use these previous concepts in analyzing our today's topic. Now we will discuss electric potential energy in uniform electric field. So for that, consider a situation that there are two plates, one is positive and the lower one is negatively charged, and let us assume that a uniform electric field E exists between these two plates. Let us consider there is a charge of Q here and the separation between the plates is 1. If I move a charge from this point toward this plate, then you know that if the charge is placed in electric field, it must be acted by a force that is Q times the field. Since field is constant everywhere, so this force is going to be constant, and if my charge moves from this plate to this plate, the displacement is y, so we can write that the work done from, suppose, a point A to a point B is force multiplied by displacement. The force will be QE into B. As I told you that my electric field is uniform, so this force must remain constant during the motion of the charge from point A to point B. It means that the force is not varying. Now, if I will take this example in a component form, this is my x component, this is my y component, the force is acting in the direction of electric field as I have taken a positive charge over here. So, my force along the y-axis will be minus of QE, and the work done along y direction means if my charge moves from B to A, then that work done will be equal to force in that direction multiplied by the separation. As you can see, this is analogous to the gravitational force on a mass m. So from that analogy we can conclude that my electric force, that is Q times the electric field, is conservative. It means that it will only depend on the initial and the final position of the charges. It will not depend on the path followed by the charges. It indirectly means that suppose my charge follows this kind of path and moves from A and reaches B, or it may take another kind of path like this, then in that case also the work done will be same, since my electric force is conservative in nature. Let us explore this idea in other way. Again, I am taking a region of uniform electric field over here, and there is a charge Q at a distance of YB. This is my point B and this is my point A, and the position of this point from this bottom plate is YA and this position is YB. So if my charge moves from point B to point A, I can write that work from B to A under the effect of this uniform electric field E will be the difference of potential energy at B minus at A. In this situation, since the work done is positive because the force is acting in the downward direction and the displacement is also in the downward direction, it means work done by electric force is positive, and the work is positive, it means potential energy decreases. Electrostatic potential energy decreases. On the other hand, if the same situation is repeated, that means my charge moves from point A to point B, so work has to be done against this electric force, and with the previous parameters we can write that work from A to B must be equal to potential energy at A minus electrostatic potential energy at B, and since work from A to B is negative, it means my potential energy must increase in this case. The idea of electrostatic potential energy is not limited in the case of uniform electric field. Indeed, we can apply this concept to a point charge in any kind of electric field. Just like, let's consider a situation that it is my point charge plus Q that is placed at a distance of R1 from this charge. It is my source charge that is producing the electric field, and let me take this charge as a test charge. Initially my test charge was at a distance of R1 from this charge Q, and I need to move it from point A to point B, and that is at a distance of R2 from this charge. As we know that if we will move away from the charge, the electric field goes on decreasing. So when my test charge will move from point A to point B, the electric field of this charge will gradually decrease. And if the electric field decreases, it means electric force also goes on decreasing. Since the force is continuously decreasing, it means it is not a constant force here. So the force is variable. So to calculate the work done, first of all, I need to take a small distance of dx at a distance of x from this charge. If my test charge is supposed to be placed here at a distance of x, then force on charge, that will be a small force, say df, can be calculated by Coulomb's law, and that is 1 by 4 pi epsilon naught. First charge q, second charge q naught divided by the square of distance. Now if my charge moves through a very small distance dx in the direction of force, so work done will be force multiplied by the distance. So I will put the value here. This is 4 pi epsilon naught q naught by x square into dx. This is the work done in displacing the charge by a small distance dx. Now, since my force is varying, so to find the net force, we have to integrate this within the limits from R1 to R2. So I will integrate this. The constant term in this can be taken out from here, and my work will be like 1 by 4 pi epsilon naught q naught integration of dx by x square R1 to R2. If you integrate this term, you will get minus of 1 by x within the limits R1 to R2, and further on applying the limits, upper limit minus lower limit, we will get 1 minus R1 by minus 1 by R2, and this is the net work done. If I will just simplify more this, we can write it as 1 by 4 pi epsilon naught q naught by R1 minus 1 by 4 pi epsilon naught by R2. And if you can see, then it is the difference of two sums, and that is difference is of the difference of electrostatic potential energy. So I can write it like this is potential energy at distance R1 minus potential energy at distance R2. Though we have taken the situation where the force is variable because my electric field was varying, then also the work done only depends on the initial and the final position, and it proves that in case of non-uniform electric field, if the work done is depending on initial and final position, it means the force that is acting on the charge is still conservative in nature. So, in a general way, we can write the electrostatic potential energy at a distance r from the pair of two charges as 1 by 4 pi epsilon naught q naught by r. So, if I am having two charges that are placed at a distance of r, then the electrostatic potential energy of that system will be 1 by 4 pi epsilon naught q1 q2, because my first charge was q, then second charge was test charge, divided by r. Here there is an important thing to know, that while calculating the electrostatic potential energy, you have to put these two charges with proper sign. For an example, if I am taking one charge as q1 and that is positive, and the second charge q2 is also positive, or you can say a pair of negative charges. So in that case, if these two charges are placed at a distance of r, the electrostatic potential energy of the system will be 1 by 4 pi epsilon naught q1 q2 by r. So for like charges, the electrostatic potential energy of the system is positive. On the other hand, if I will take pair of the charges that are opposite in nature, so for this system, electrostatic potential energy will be q1 minus q2 divided by r. So while calculating the electrostatic potential energy, just keep in your mind that you have to place the value of the charge with proper sign. Now we will deal the situation where there is a number of charges at a place. Consider the situation that I am having four charges here, and the distance of q2 from q1 is r1, distance of q4 is r3, and distance of q3 is r2 here. So for this system of charge, we can calculate the electrostatic potential energy in an easiest way. First of all, we will just take the pairs of the charges. The maximum possible pair that we have here is 3. One pair is this one, the second pair is this one, and the third pair is this one. So we will calculate the potential energy for pair of charges or for all kind of pairs that are available in the situation, and we will add. So since we have 3 pair of charges over here, so I will add these 3 and we will write the expression here for this one. This is K, that means 1 by 4 pi epsilon naught Q1 Q2 divided by R1 plus for second pair we can write K times first charge, second charge divided by the separation, and similarly for the third charge it will be K product of charges divided by separation. So by doing this we can find out the total electrostatic potential energy of the system. Now what if I am having n number of charges like this? So if you can see that charge Q1 is common because I have taken the pair with respect to this charge. So in general we can write it as sigma K Q1 and this Qi, because the second charge is going to vary, divided by Ri, the distance will also change, and I extends from 1 to n, or in other way we can take K Q1 is common and this is going to be Qi I1 to n. So if you are having n number of charges, simply find the electrostatic potential energy for each pair and add them algebraically. Now consider a problem here. For an example, say I am having a square of side A and 4 equal charges Q are placed on its vertices, and I need to find out the electrostatic potential energy of this system. So as I told you that first of all we will find the maximum number of pairs. So I am having one pair here, second pair here, third pair here, fourth pair here, and very important, these 2 pairs. One is this one, diagonally opposite pairs. So we are having 6 pairs of charges. So first of all, for these 2 charges I can write K times first charge, second charge divided by the separation, plus the same will be for here too, because the charges are equal and the separation is same. The same is here and the same is here. So we are having 4 pairs for which pair of charge and the separation is same. So simply I will multiply it by 4. So this will give me the electrostatic potential energy of these charge pairs. Now 2 are left. So we know that the diagonal is going to be root 2 times A. So for these 2 pairs I can write K first charge, second charge divided by the separation, and once again as these charges are at an equal separation, so I will just multiply by 2, which on simplifying gives me K Q square divided by A, and this is going to be 4 plus 2 by root 2. Since it is the energy, so we can write its unit as joule. Now we will discuss electric potential. Electric potential at a point in electric field is the electrostatic potential energy per unit charge. That is, the potential at any point is the electrostatic potential energy per unit charge. Since electrostatic potential energy and the test charge that I have taken both are scalar, so electric potential is a scalar quantity and its unit can be joule per coulomb, as joule is the unit of potential energy and coulomb is the unit of charge it is having. And another unit, and that is called volt. Now suppose, consider the previous situation where the work was equated with the potential energy. So we know that work from point A to B, suppose my charge moves from point A to B, then I need to calculate the work done per unit charge. So you know that this can be written as change in potential energy divided by charge. This I can write as UB minus QA divided by Q naught, and it is UA by Q naught minus UB by Q. So you can see clearly that work done in moving a charge from point A to B per unit test charge is equal to the difference of these two quantities, and with the difference to the definition of electric potential, you can see that it is the potential for a point A and it is the potential for a point B. So I can write it as at A minus potential at B. So the potential difference, this term is called potential difference, or in general form we can also write it as VAB. VAB is the potential of A point with respect to point B. So if I will move a charge from point A to point B, then the work done in moving the test charge from point A to point B per unit charge gives me the potential difference between their points. Now, as you can see, this is the basic definition of electric potential. So we have the value of electrostatic potential energy at a location R from a given charge, and U was 1 by 4 pi epsilon naught Q naught by R. So if I will use the value of this electrostatic potential energy in this relation, we can find out the potential at a distance of R from a charge that is producing the electric field as U by Q naught, which on simplifying gives 1 by 4 pi epsilon naught Q by R. And it is very clear from here that potential at a distance of R decreases with distance R, like this expression. And if my distance is infinity, it means my second point is at distance infinity, or you can say if the another test charge is kept at infinity, then this potential is going to be C. So at a point that is located at infinity, the potential is 0. Now what will happen if I have to calculate the potential at a point surrounded by number of point charges? So suppose there is a point P where the electrostatic potential is required, and we are having so many charges around it at different locations, R1, R2, R3. So the process is same. If we need the net potential at this point due to all these surrounding charges, so I will simply add the potential due to all these charges algebraically at that point, and that will give me 1 by 4 pi epsilon naught sigma Qi by Ri, where I ranges from 1 to n. So by this formula we can simply calculate the net electric potential at any point by number of charges. what will happen if my charge is not discrete charges, they are continuous charges? So in case of continuous charges, the electrostatic potential, the electric potential can be calculated by integrating this term. So in case of continuous charge distribution, we will just integrate this term to find out the net electric potential at any point. Now, there is another method to find out the electric potential at a point. Consider a charge Q that is producing electric field around it, and I need to find out the potential at this point P, which is at a distance of R from this charge. So for calculation purpose, first of all I will put a test charge over here at a distance of x from this charge, and we know that from Coulomb's law I can find out the value of the force that will act on this test charge, and definitely it is going to be away, and that is Q naught by x. If I will displace it in the direction of electric field by a distance of dx, the work done will be the force times the displacement. So this is Q naught by x square into dx. Now, if I need the potential at this point, say my test charge moves from this point to a point at infinity, so the net work done in that process will be integration from R to infinity, and this will give me the potential at this point P minus the potential at infinity as per the definition. Since the definition was the potential difference is work done by test charge. So if I will divide these terms, so it will be kq integration 1 by x square dx r to infinity. We know that potential at infinity is 0, so it is the potential only at this point, and that is kq. This on simplifying gives 1 by x minus of, and this is r to infinity, and if you will simplify you will get k q by r. Using the value of k, this is 1 by 4 pi epsilon naught q by r, and this is the potential at a distance of r from a test charge. So by this way also we can find out the electric potential at a point. Now we will find the electric potential due to dipole. So as we are aware of that a dipole consists of two equal and opposite charges separated by small distance, say 2m. First of all, we will find the potential due to dipole at a distance of r from the dipole. So the method is very easy. First of all, I will not treat it like a dipole. I will just treat this situation like I am having two charges here, and we need to find out the potential at this point P. So first of all, I will find out the potential due to negative charge at this point, potential due to positive charge at this point, and simply we will add them. So the potential due to negative charge will be k times the charge divided by separation, and this distance will be r plus l from this point to this charge. Now the important thing is, since my charge is negative, so I will put a minus sign over here, since potential is the ratio of potential energy per unit charge, and I told you that in formula of electrostatic potential energy we take charge with proper sign. Similarly, we can find out the potential at P due to this positive charge, and that will be k times the charge, that is a positive charge, divided by the separation, and that will be r minus l. So the net potential is the sum of potential due to negative charge and the positive charge. So I will put the value here. You will get k times q 1 by R plus L minus plus 1 by R minus L. If you will simplify it, you will get V net equals to K cube. This is R plus L, R minus L, and if you will simplify it, you will get 2L here. So Q into 2L is nothing but the electric dipole moment. So I will write it as P, and this is R square minus L square. If I will use the value of K, so this is the net potential at this point due to dipole. Now just consider that my point is very large distance, at a very large distance from this dipole. So I can take that my R is greater than L, or L is less than R, and we know that L square by R square will be very less than 1. So I can neglect this term here. 1 by 4 pi epsilon naught P by R square in bracket 1 minus L square by R square. As per this condition, L square by R square can be neglected. So the remaining term will be 1 by 4 pi epsilon naught P by R square. So this is the potential due to dipole along axial position. Now we will find out the electric potential due to dipole along equatorial line. So this is my dipole, and this is the equatorial line. Let this is a point P at a distance of R, and we need to find out the net electric potential at this point due to this dipole. So as I told you that first of all we will find the potential due to negative charge, then due to positive charge, and we will add them, and for that we need the distance of this point from the charge. So from calculation it will be root R square plus L square, and the same distance will be here too. Now if we will calculate the potential due to negative charge, this is K times charge divided by distance, and that is going to be under root of R square plus L square. Similarly, the potential due to positive charge here, the distance is this, so this is going to be K plus Q divided by root R square plus L square, and net potential is the sum of potential due to positive and negative charges. As you can see clearly, these two are same terms. One is positive, another is negative, so this net potential is going to be 0. It means the potential at every point along the equatorial line of the dipole, the potential is 0. It means the potential here will also be 0, the potential here, and if I will extend it downwards, the potential at all the points along this equatorial line will be 0.